The water wheel turned steadily through the January cold, its wooden paddles catching the creek flow, while inside the cabin Alistair Mackenzie sat in shirt sleeves despite the Montana winter raging outside. 3 cabins down the valley, Declan Murray was burning his last cord of firewood and wondering how the Scotsman stayed warm using half the wood everyone else required. If you're watching from somewhere cold tonight, drop a comment and let us know. And if stories about frontier ingenuity speak to you, subscribe, because tomorrow's tale is even more unexpected than this one. The year was 1839. The Rocky Mountain fur trade was entering its final years, though the men who trapped beaver along the cold tributaries of the Yellowstone River didn't know it yet. They knew only that winters in the mountains could kill you as surely as grizzly bears or hostile encounters with various tribes protecting their territory. Cold was the silent killer, the one that crept through cabin walls and found you in your sleep. Alistair Mackenzie had survived 7 winters in what would eventually become western Montana territory. He was 32 years old, a transplant from the Scottish Highlands who had come west in 1832, seeking the same thing that drew most mountain men to the wilderness: freedom, profit, and distance from civilization's restrictions. He had found all 3, along with dangers he had never imagined during his youth in Inverness. The trappers who worked the northern Rockies lived in a world of extremes. Summer temperatures could reach 90 degrees. Winter cold regularly dropped to 20 below zero, sometimes colder. A man could make a fortune in beaver pelts during a single good season or lose everything to a single bad decision. The margin between survival and death was often measured in inches: the thickness of a cabin wall, the depth of snow that made trap lines inaccessible, the distance between your shelter and the nearest help when something went wrong. Most mountain men accepted these realities as the cost of their chosen life. They built their cabins using methods that had been passed down through generations of frontier settlement. Find a good location near water and timber. Cut logs. Notch them at the corners. Stack them into walls. Chink the gaps with mud and moss. Build a roof from poles and bark. Add a fireplace if you had the skill and materials. The entire process took 4 to 5 days with 2 men working, maybe a week if you worked alone. The resulting structure would keep out wind and rain. It would provide a place to sleep, store supplies, and wait out the worst weather. That was enough for most men. Alistair had built his first cabin using exactly those methods back in 1832. He had built 2 more in the years since, each time following the same basic pattern. Each cabin had served its purpose adequately, but adequate meant something different when you were trying to survive a Rocky Mountain winter. Adequate meant you burned enormous quantities of firewood. Adequate meant you woke up with frost on your blankets despite a fire burning all night. Adequate meant the area within 5 feet of your fireplace was uncomfortably hot, while the corners of your cabin remained cold enough to freeze water. Adequate meant you accepted these conditions because every other trapper accepted them. Until the winter of 1838 taught Alistair Mackenzie that adequate wasn't actually good enough, and that lesson came at a price he would never forget. Eamon Sullivan had been Alistair's trapping partner for 3 seasons. The Irishman had come west from St. Louis in 1835, cheerful and competent, good with traps and better with stories. They had worked well together, splitting the labor and profits equally, watching each other's backs in country that could kill a solitary man without warning. Eamon had built his cabin a quarter-mile from Alistair's, close enough for companionship, but far enough for privacy. The winter of 1837 to 1838 was brutal, even by Montana standards. Snow came early in October and never stopped. Temperatures dropped to 30 below and stayed there for weeks. The trappers hunkered in their cabins, venturing out only when absolutely necessary to gather firewood or check on each other. Alistair visited Eamon's cabin every few days, sharing coffee and conversation, breaking the isolation that could drive men mad during the long, dark months. On February 9, 1838, Alistair made his regular visit. He found Eamon dead. The Irishman was in his bed, wrapped in every blanket he owned, frozen solid. The fireplace still had wood stacked beside it. Eamon's rifle was loaded and within reach. There had been no accident, no attack, no dramatic crisis. The man had simply gone to sleep and never woken up. The fireplace showed evidence of a fire the previous night. Eamon had burned wood, kept himself warm enough to function, then climbed into bed as he always did. But Montana cold in February didn't care about fireplaces or blankets. The cabin's single heat source created a sphere of warmth that extended maybe 6 feet. Beyond that, the temperature dropped steadily. In the corners farthest from the fire, ice formed on the interior walls. Eamon's sleeping area was 12 feet from his fireplace. He had frozen to death 15 feet from a stack of firewood in a cabin he had built with his own hands, following methods that every experienced frontiersman knew and trusted. Alistair buried his friend on a hillside overlooking the creek where they had trapped together. He marked the grave with stones and spent that night in Eamon's cabin, unable to sleep, trying to understand what had happened. The fire had been adequate. The cabin construction was adequate. Everything had been done correctly, according to accepted practice, and Eamon Sullivan was still dead. That night, sitting in a dead man's cabin with cold creeping through gaps in the log walls. Despite the fire burning in the hearth, Alistair began to understand something that would obsess him for the next 18 months. The problem wasn't the amount of heat being generated. The problem was how that heat moved through the space. Fire created warmth, but warmth didn't travel on its own. It stayed where it was created, radiating outward until distance and cold air defeated it. A cabin with a roaring fire could still have frozen corners. A man could burn a month's worth of wood in a week and still wake up cold. The heat was there, abundant and available, but it wasn't reaching the places where men actually slept. Alistair spent the remainder of that winter obsessed with a problem most mountain men never thought about. How did heat actually move inside a cabin? He started paying attention to things he had previously ignored. Smoke from his fireplace rose to the ceiling, then spread outward, creating a layer of warm air above and cooler air below. Heat radiated from the fire in straight lines, warming whatever it touched directly but leaving shadows of cold behind any obstacle. The warmest air in his cabin was always at ceiling height, 8 feet above where he slept. The coldest air pooled at floor level and in corners farthest from the fire. He began measuring temperatures using a simple thermometer he had purchased years earlier for monitoring weather. The readings were stark. 3 feet from his fireplace, the temperature reached 70 degrees. 6 feet away, it dropped to 50. In the corner where he stored his furs, it never rose above freezing even with a fire burning continuously. He was living in a structure with a 40-degree temperature variation from one end to the other, all within a space measuring 16 feet by 20 feet. Other trappers dealt with this problem by burning more wood. If the corners stayed cold, you slept closer to the fire. If your sleeping area was too far from the hearth, you built a bigger fire. The solution was always more fuel, more heat, more consumption. Alistair had followed this logic for 7 years without questioning it. But watching how quickly his woodpile diminished during cold months made him reconsider the approach. A mountain man working alone could cut and split about half a cord of firewood in a full day of hard labor. During the coldest months, Alistair burned approximately 1 cord per week to maintain barely adequate warmth. That meant 2 days of every week spent cutting wood just to stay alive. 2 days not spent trapping, not spent hunting, not spent on any productive activity beyond fuel gathering. Multiply that across a 5-month winter, and the math became depressing. 40 days of labor producing nothing except the ability to survive until spring. The inefficiency bothered him more than the labor. He was generating abundant heat. The fire produced more than enough warmth to heat his entire cabin comfortably, but most of that warmth never reached the areas where it was needed. It rose to the ceiling and stayed there, or radiated into spaces where nothing important happened. Meanwhile, the corners where he stored food and supplies remained cold enough to freeze water. He was working twice as hard as necessary because the heat he created wasn't being used effectively. Alistair started thinking about movement. Heat didn't move on its own, but air did. Wind moved air across landscapes. Temperature differences created air currents. He had seen this principle in operation countless times without recognizing its significance. Warm air rising from a fire, cool air rushing in to replace it, the constant circulation that occurred naturally wherever temperature differences existed. The question that began to form in his mind was simple but radical. What if he could force air to move inside his cabin? Not rely on natural convection, but actively push air from the warm areas to the cold areas? Spring came late in 1838. Alistair finished his trapping season in May and left the mountains in early June with his furs packed on 2 horses. The journey to St. Louis took 3 weeks by the most direct route, riding hard through country that was becoming increasingly settled as emigrants pushed westward. He reached the city in late June and sold his pelts to a trading company for a decent price. Most trappers would have spent the next few weeks drinking, gambling, and enjoying civilization's pleasures before heading back to the wilderness. Alistair spent his time studying buildings. St. Louis in 1838 was a growing city, a jumping-off point for western expansion and a center of river commerce. Construction was constant. Warehouses rose along the waterfront. Mills processed grain brought down from northern farms. Foundries produced iron goods for the frontier trade. Alistair watched all of it with the focused attention of a man trying to solve a specific problem. He wasn't interested in architecture or engineering as abstract concepts. He wanted to understand how things moved. He spent 2 days observing a grain mill on the edge of town. The mill used a water wheel to power grinding stones, a technology that had existed for centuries. Alistair wasn't interested in the grinding. He was interested in the wheel itself, how it captured the energy of flowing water and converted it into rotational motion, how that rotation was transmitted through axles and gears to drive machinery, how the entire system operated continuously without human effort, powered by nothing more than a creek that flowed whether anyone used it or not. The mill owner noticed Alistair's persistent presence and eventually asked what he wanted. Alistair explained that he was trying to understand how the wheel worked. The owner, amused by a mountain man's sudden interest in milling technology, gave him a tour. He explained the mechanics of overshot, wheels versus undershot wheels. He showed Alistair the bearing system that allowed the heavy wheel to rotate with minimal friction. He demonstrated how gear ratios could increase or decrease rotational speed depending on the work being performed. Alistair asked about air movement. The owner looked confused until Alistair clarified. Did the mill owner ever use the wheel's rotation to move air, to circulate it through a space? The owner said no, but the question made him think. He walked Alistair to a different part of the mill where a belt-driven fan moved air through the grain drying room. The fan was simple, just wooden blades mounted on an axle, but it moved a remarkable amount of air when spinning. The owner explained that air movement was critical for drying grain evenly. Without circulation, the grain nearest the heat source would dry too quickly, while grain in the corners would mold. That conversation changed everything. Alistair suddenly understood that his cabin heating problem and the mill's grain drying problem were identical. Both involved getting heat distributed evenly through a space. The mill solved it with forced air circulation. A fan driven by the water wheel moved air continuously, preventing hot spots and cold spots. The principle was simple. The application was proven. The question was whether it could be adapted to a frontier cabin in the Rocky Mountains. Alistair spent the next week in St. Louis gathering supplies and information. He visited a foundry and purchased iron bearings designed for heavy continuous use. He bought canvas belting used in mill machinery. He acquired tools he had never owned before, including specialized augers for boring precise holes through thick wood, chisels designed for cutting mortises, and a draw knife for shaping curved surfaces. He purchased nails by the pound, expensive on the frontier, but necessary for what he was planning. The trading post clerks thought his orders were strange. Mountain men typically bought powder, lead, coffee, salt, and basic staples. They didn't buy industrial hardware or specialized carpentry tools. When Alistair added a technical manual on water wheel construction to his purchases, the clerk asked directly what he was building. Alistair said he was trying to heat a cabin more efficiently. The clerk nodded slowly, clearly unconvinced that any of these items would help with that goal. Other trappers preparing for the return journey noticed Alistair's unusual supplies. A French-Canadian named Baptiste Moreau examined the iron bearings and asked if Alistair was planning to build a mill. Alistair said no, just a cabin. Baptiste laughed and said that was the most expensive cabin in the Rocky Mountains. Another trapper named Jacob Vandenberg looked at the canvas belting and asked what possible use that had in the wilderness. Alistair didn't explain. He had learned that trying to describe what he was planning only generated mockery and arguments. The supplies were heavy. The iron bearings alone weighed 30 pounds. The tools, nails, and hardware added another 40 pounds. Alistair ended up purchasing a third pack horse just to carry everything back to the mountains. The cost was substantial, eating into his first sale profits. A practical man would have questioned whether this investment made sense. Alistair wasn't thinking about practicality. He was thinking about Eamon Sullivan frozen in his bed and the 40 days every winter spent cutting firewood just to survive. He left St. Louis in mid-July and headed west. The return journey was slower, with 3 horses and heavy packs. He reached the mountains in early August, riding back into country that felt more like home than any place he had known in Scotland. Other trappers were already returning to their territories, preparing for the fall season. Alistair passed several familiar camps and stopped briefly to share news from civilization. The conversations always turned to his unusual cargo. Declan Murray, an Irish trapper who worked the same drainage system as Alistair, examined the tools and hardware with obvious skepticism. He asked flat out what Alistair was doing with mill equipment in the mountains. Alistair explained that he was going to build a cabin that stayed warm without burning excessive firewood. Declan laughed hard enough to spook the horses. He said that was the stupidest thing he had heard all year. A cabin stayed warm when you burned enough wood. That was how it worked. That was how it had always worked. Spending a fortune on iron bearings wouldn't change basic reality. Alistair returned to his territory in mid-August 1838 and immediately began scouting for a new cabin location. Most trappers built near water for convenience, easy access to drinking water, proximity to beaver ponds, level ground that simplified construction. Alistair was looking for something specific that had nothing to do with convenience. He needed flowing water with reliable year-round volume and sufficient elevation drop to power a wheel. He spent 2 weeks studying the creeks that drained his trapping area. He measured flow rates by timing how long it took floating sticks to cover known distances. He estimated volume by observing water depth and channel width. He noted which streams ran strong in August during the lowest water period of the year. If a creek flowed well in late summer, it would flow even better during spring runoff and fall rains. Year-round reliability was critical. A water wheel that only worked part of the year was useless. The site he eventually selected was a place he had passed hundreds of times without considering it for construction. A fast creek tumbled down a rocky slope through dense pine forest. The creek had cut a channel through bedrock, creating a natural drop of approximately 8 feet over a distance of 30 feet. The current was strong even in August. During spring runoff, it would be powerful. The location had obvious disadvantages. The slope made construction difficult. The rocky ground would complicate foundation work. The nearest flat area suitable for a cabin was only 20 feet from the creek's edge, far closer than any sensible builder would choose. But the location had exactly what Alistair needed: reliable water flow, sufficient elevation drop to power an overshot wheel, a natural channel that could be diverted to feed water to the wheel, and enough space between the creek and a potential cabin site to position a wheel and mechanical coupling. The disadvantages that would deter other builders didn't concern him. He wasn't building a conventional cabin. Malcolm Fraser, a Scottish trapper who worked adjacent territory, visited during Alistair's site survey. Malcolm had built his own cabin 3 years earlier following standard methods. When he saw where Alistair was planning to build, he was openly confused. The site was too close to the water. Spring flooding would threaten the structure. The slope made everything harder. There were better locations within a quarter mile, flat areas with good drainage and safe distance from the creek. Why choose this spot? Alistair explained about the water wheel and the heating system he planned to build. Malcolm listened carefully, asked several questions about the mechanics, then gave his assessment. The idea was interesting in theory, but impractical in execution. Water wheels were large, heavy, and required constant maintenance. Building one was specialized work that few men knew how to do properly. Even if Alistair succeeded in building a functional wheel, connecting it to a cabin's heating system seemed impossibly complex. And all of this effort to solve a problem that already had a simple solution. Burn more wood. Alistair began construction in late August 1838, with a foundation unlike anything other trappers built. Standard cabins sat directly on the ground or on a few flat stones that provided minimal leveling. Alistair designed a raised platform that would elevate his entire cabin 3 feet above ground level. The elevation served multiple purposes. It positioned the cabin above potential floodwater during spring runoff. It created clearance for the mechanical connection between the water wheel and the interior, and it established a specific height relationship between the wheel's axle and the cabin floor that his calculations required. He started by clearing the site of vegetation and loose soil until he reached bedrock or solid ground. Then he gathered stones from the creek bed, selecting flat pieces that could be stacked stably. The stonework took 3 weeks. He built 8 pier foundations, each approximately 4 feet tall, arranged in a rectangular pattern that would support the cabin's floor joists. Each pier had to be precisely the same height. He used a level made from a glass tube partially filled with water, checking and rechecking until all 8 piers were within a ½ inch of each other. Other trappers who passed by thought the foundation work was absurd. Declan Murray stopped one afternoon and watched Alistair adjust a pier by removing and replacing stones to achieve perfect level. Declan said this was exactly the kind of nonsense that happened when educated men tried to do practical work. A cabin didn't need to be level. It needed to keep out rain and wind. Spending 3 weeks on a foundation was 3 weeks not spent cutting firewood for the coming winter. Alistair didn't argue. He had learned that explaining his reasoning only invited more criticism. Instead, he continued working with methodical precision. Once the piers were complete, he laid heavy timber joists across them, creating a platform frame. The joists were hewn from straight pine logs, shaped with his draw knife to create flat-bearing surfaces. He notched them where they crossed, creating a rigid grid pattern. Then he laid floor planks across the joists, spacing them tightly and pegging them in place with wooden pins. The result was a floor platform elevated 3 feet above ground, perfectly level, and strong enough to support the weight of log walls and roof. The space beneath the platform would remain open, allowing air circulation and preventing moisture accumulation. The elevation also meant that Alistair could route mechanical connections underneath the floor where they would be protected from weather and debris. The foundation work consumed most of September. By the time Alistair was ready to begin wall construction, other trappers had finished their cabins and started preparing trap lines for the fall season. Malcolm Fraser visited again and admitted that the foundation was impressively built, even if it seemed excessive. The piers were solid. The platform was level and strong. But Malcolm questioned whether all this precision mattered. A cabin was a simple structure. It didn't require the exactness of a mill or a bridge. Alistair's response was simple. He wasn't building a simple cabin. While the foundation settled, Alistair began building the water wheel itself. He had studied wheel construction in St. Louis and purchased a technical manual that explained the mathematics of diameter, bucket design, and rotation speed. An overshot wheel, where water fell onto the top of the wheel and filled buckets that pulled the wheel around by weight, was the most efficient design for the elevation drop he had available. But efficiency meant nothing if the wheel couldn't be built properly using frontier materials and tools. He started by felling a massive pine tree for the wheel's axle shaft. The tree had to be straight, at least 14 inches in diameter, at the base, and free of knots or twists. He found a suitable tree a quarter-mile from his building site and spent 2 days cutting it down, trimming it, and dragging it to his work area using his horses. Once positioned, he used his draw knife to shape the trunk into a cylindrical shaft, removing bark and sapwood until he had a smooth, round beam 12 inches in diameter and 10 feet long. The wheel itself required precision carpentry that tested every skill Alistair possessed. He built it in segments, constructing 2 circular rims from bent wood, then connecting them with radial spokes that extended from the central axle to the outer rim. Each spoke had to be exactly the same length and angled precisely to create a true circle. He shaped them from straight-grained oak, using templates to ensure consistency. The spokes were mortised into the axle shaft and pegged to the rim pieces with wooden pins driven through pre-drilled holes. Between each pair of spokes, he built buckets that would catch falling water. The buckets were simple wooden boxes, open on one side, angled slightly to hold water as the wheel rotated. As each bucket reached the bottom of its arc, it would dump its water and rise empty on the opposite side. The weight of water filled buckets on the descending side would overbalance the empty buckets rising on the opposite side, creating continuous rotation. The mathematics of this were ancient, but executing them accurately required constant measurement and adjustment. The bearing system was where Alistair's expensive iron purchases proved essential. A wooden axle rotating under load would quickly wear through wooden bearings, creating friction and eventual failure. He had purchased iron sleeve bearings in St. Louis, cylindrical pieces that would surround the axle shaft and allow it to rotate with minimal friction. He built heavy timber supports to hold these bearings, creating an A-frame structure similar to what he had seen at the St. Louis mill. The bearings were mounted in wooden blocks that could be adjusted to ensure the axle remained level and centered. By mid-October, the wheel was complete. It measured 9 feet in diameter and weighed approximately 400 pounds. Alistair had built it on the ground near where it would be installed, but moving it into position required careful planning. He constructed a temporary timber crane using the same A-frame principle as the bearing supports, then used his horses to lift the wheel and maneuver it onto the bearing mounts. The installation took an entire day, and nearly ended in disaster when one of the support timbers cracked under the weight. The water wheel was functional but useless without a way to transmit its rotation into the cabin. This was the problem that had consumed Alistair's thinking for months. He needed to run the wheel's axle shaft through the cabin wall in a way that allowed free rotation while preventing water, air, and cold from entering through the penetration. Standard construction methods offered no solution because no one built cabins with rotating shafts penetrating their walls. Alistair's solution combined principles from mill construction with materials available on the frontier. He extended the wheel's axle shaft beyond the bearing supports, creating a 10-foot extension that would reach from the wheel to the cabin wall and continue inside. This extension had to be perfectly aligned with the wheel's main axle to prevent wobbling or binding. He achieved this by carefully selecting and shaping the wood, ensuring the grain was straight and the diameter consistent. Where the shaft would penetrate the cabin wall, he built a special housing from thick timber. The housing was essentially a box mortised into the cabin's log wall, creating a reinforced opening large enough for the shaft plus clearance for rotation. Inside this box, he installed a second set of iron bearings that would support the shaft at the wall penetration point. These bearings would carry significant load because the shaft extended 10 feet inside the cabin, creating leverage that could bind the rotation if not properly supported. The waterproofing challenge was solved with layers of different materials. Around the shaft where it passed through the wall housing, he wrapped canvas soaked in pine pitch. The pitch hardened into a flexible but waterproof seal that could accommodate the shaft's rotation while blocking moisture. Outside the housing, he built a wooden collar that directed any water running down the shaft away from the penetration point. Inside, he created a similar collar that would catch any condensation or water that penetrated the outer seals. The entire coupling assembly took 2 weeks to build and install. Every component had to be shaped, fitted, tested, and adjusted. The bearings had to be positioned exactly to prevent binding. The waterproof seals had to be flexible enough to allow rotation, but tight enough to prevent leaks. The housing had to be strong enough to support the shaft's weight and rotation forces while being integrated into the cabin's structural wall. When Alistair finally tested the system by diverting water onto the wheel, the results were imperfect but promising. The wheel rotated smoothly. The shaft turned inside its bearings with acceptable friction. The coupling transmitted rotation from outside to inside without visible water penetration, but the system was noisy. The bearings created a grinding sound. The shaft flexed slightly under load, causing periodic binding, and the rotation speed was faster than Alistair had calculated, which would create problems for the interior fan system. He spent another week making adjustments. He packed the bearings with rendered animal fat to reduce friction and noise. He added support braces to prevent shaft flex. He modified the water flow to the wheel, reducing the volume slightly to slow rotation speed. Each change required testing and further refinement. By early November, he had a coupling system that rotated quietly, smoothly, and reliably. The shaft extended 8 feet inside the cabin, ready to drive whatever mechanism he would attach to it. Inside the cabin, Alistair faced his most complex engineering challenge yet. The rotating shaft had to drive a fan system that would move air from the fireplace area throughout the entire interior space. The fan had to move sufficient air volume to make a difference in temperature distribution, but not so much that it created uncomfortable drafts or excessive noise. And the entire system had to be built from wood, leather, and basic materials available on the frontier. He started by building the fireplace in the corner farthest from where the shaft entered. This placement was counterintuitive. Most cabins put the fireplace near the door for ease of wood delivery and ash removal. Alistair positioned his fireplace to create maximum distance between the heat source and the fan system. This distance would force the circulated air to travel the full length of the cabin, ensuring even distribution. The fan itself was surprisingly simple in concept but demanding in execution. He built it using the design he had seen in the St. Louis grain mill. 4 wooden blades mounted on a central hub, angled to push air when rotated. The blades were shaped from thin pine planks, curved slightly to improve airflow. Each blade was 2 feet long and 6 inches wide. The hub was a solid wooden cylinder that mounted onto the rotating shaft using a keyed connection that prevented slipping. The critical innovation was the ductwork. Alistair built a wooden hood over the fireplace that collected rising hot air. From this hood, he constructed a channel made from thin planks that directed air toward the fan location. The channel was essentially a wooden tube, 12 inches square, that ran along the cabin's ceiling. As the fan rotated, it pulled air from this channel and pushed it through a second channel system that distributed air throughout the cabin. The distribution channels were the most complex part. He built 3 separate ducts that branched from the main fan outlet. One ran toward the sleeping area, one directed air toward the storage corner, one vented near the door where cold air naturally entered. Each duct had adjustable wooden dampers that allowed Alistair to control airflow to different areas. This adjustability was crucial because he didn't know how much airflow each area would need until the system was operating. The gearing presented another challenge. The water wheel rotated at approximately 20 revolutions per minute, which was too fast for the fan. A fan spinning that quickly would create a windstorm inside the cabin. Alistair needed to reduce the rotation speed by roughly half. He solved this with a simple gear system using wooden wheels of different diameters. The shaft from the water wheel drove a large wooden gear wheel. This wheel engaged a smaller gear mounted on the fan's hub. The size ratio created the speed reduction he needed. By late November, the interior system was complete and ready for testing. The fireplace was built and functional. The fan was mounted and connected to the drive shaft. The ductwork was installed with all joints, sealed using clay and canvas. The dampers were adjustable and properly positioned. Alistair lit his first fire in the new cabin and engaged the water wheel. The fan began to rotate. Air started moving through the ducts, and for the first time, warm air from the fireplace flowed to every corner of the cabin interior. The completed cabin drew visitors throughout December 1838. Trappers traveling through the area stopped to see what Alistair Mackenzie had built, and their reactions ranged from bewilderment to open mockery. The structure looked wrong from the outside. The elevated foundation made it appear precarious. The water wheel, positioned so close to the living space, seemed dangerous. The wooden shaft penetrating the wall violated every principle of sound cabin construction. And the constant sound of the wheel turning, a rhythmic creaking and splashing, announced the cabin's presence from 100 yards away. Declan Murray became the loudest critic. He visited 3 times during December, each visit producing new complaints. The cabin was too complicated. The maintenance required would be endless. The water wheel would freeze solid during the coldest weather, destroying the entire system. The mechanical components would wear out within a year, and most fundamentally, the whole elaborate construction was solving a problem that didn't exist. Cold cabins were kept warm by burning more wood. That was frontier reality. Building a mill attached to your home was the fantasy of someone who had spent too much time alone in the mountains. The nickname started as a joke, but spread quickly through the trapping community. Declan called it Mackenzie's Folly during a gathering at Cormac O'Neill's trading post. Other trappers picked up the phrase. Within weeks, anyone discussing Alistair's cabin used the term. Mackenzie's Folly became shorthand for wasted effort, overcomplicated solutions, and the kind of thinking that happened when educated men tried to improve things that didn't need improving. Malcolm Fraser offered a more measured assessment, but still expressed doubts. He visited in late December and spent several hours examining the construction. He acknowledged the quality of the workmanship. The foundation was solid. The wheel was well built. The mechanical coupling showed genuine engineering skill. But Malcolm questioned the underlying assumption. Was heating inefficiency really a problem worth solving? Mountain men had survived for generations using simple cabins and adequate firewood. The system Alistair had built might work perfectly, but it required months of labor and expensive materials. A trapper could cut enough firewood to heat a standard cabin for an entire winter in less time than Alistair had spent building his wheel system. The criticism bothered Alistair less than he expected. He had anticipated mockery and prepared for it emotionally. What surprised him was how quickly the judgment became absolute. Other trappers didn't. Wait to see if the system worked before deciding it was foolish. They made their assessment based purely on the fact that it was different from accepted practice. Innovation on the frontier was acceptable only if it produced immediately obvious advantages. A heating system that required seeing it operate through an entire winter before its benefits became clear was too abstract for most men to evaluate fairly. Alistair spent the first week of January 1839 living in his new cabin and learning how the system actually performed under real winter conditions. The initial results were mixed. The water wheel rotated reliably, powered by creek flow that remained strong despite freezing temperatures. The mechanical coupling transmitted rotation smoothly into the interior. The fan turned at the correct speed, moving air through the duct system, but the heat distribution was uneven in ways Alistair hadn't anticipated. The problem was airflow balance. The duct running to the sleeping area received too much air, creating an uncomfortable draft. The storage corner received too little, remaining noticeably colder than the rest of the cabin. The area near the door, where cold air naturally infiltrated, needed more circulation than the current damper settings provided. Alistair spent 3 days adjusting the wooden dampers in each duct, opening some and closing others, trying to find the combination that would distribute heat evenly throughout the space. He also discovered issues with the fan blade design. The blades he had carved were slightly unbalanced, creating vibration as they rotated. The vibration wasn't severe enough to damage anything, but it produced a rhythmic humming that made sleeping difficult. He removed the fan, carefully shaved wood from the heavier blades until they balanced, then reinstalled it. The vibration decreased, but didn't disappear entirely. He realized he would need to rebuild the fan with more precision when weather permitted. The fireplace hood also required modification. Alistair had designed it to collect rising hot air, but he hadn't accounted for smoke. The hood captured smoke along with heat, and the fan system distributed smoky air throughout the cabin. After 2 days of living in a smoke-filled space, he redesigned the hood to allow smoke to rise naturally to the chimney while only capturing the hot air layer below the smoke. The modification worked, but reduced the amount of heat the system could capture. Despite these problems, the basic principle was proving sound. Even with imperfect airflow balance and the smoke issue, the cabin maintained more even temperatures than any structure Alistair had previously occupied. The corners that would normally freeze remained above freezing. The sleeping area, 12 feet from the fireplace, stayed comfortably warm, and most significantly, he was burning noticeably less firewood than in previous winters. He began keeping detailed records. Each day he noted the outside, temperature, the amount of wood burned, and temperature readings from different locations inside the cabin. The data showed patterns. On days when outside temperature dropped below zero, a standard cabin would require burning approximately 1/8 of a cord of wood to maintain minimal warmth. Alistair's cabin maintained superior warmth using roughly half that amount. The fuel savings were measurable and significant. By mid-January, after 2 weeks of continuous operation and constant adjustments, Alistair had the system operating smoothly. The dampers were properly balanced. The fan vibration was minimal. The fireplace hood captured heat without smoke. The water wheel turned reliably day and night, requiring no attention beyond occasionally clearing ice from the buckets during the coldest periods. The winter of 1839 to 1840 became Alistair's testing ground for proving what his system could do. January brought sustained cold, with temperatures regularly reaching 15 to 20 below zero. February was worse, with a brutal stretch where the thermometer didn't rise above zero for 12 consecutive days. These were conditions that tested every cabin's ability to keep its occupant alive, and they provided the perfect comparison between Alistair's approach and traditional methods. Alistair continued his meticulous record-keeping. Every morning he recorded outside temperature, inside temperature at 3 locations within his cabin, and the amount of firewood consumed in the previous 24 hours. He measured his woodpile weekly to track consumption rates. The data accumulated into an undeniable pattern. His cabin used roughly 40 to 50% less firewood than he had burned in previous winters, while maintaining superior interior comfort. The temperature distribution data was particularly striking. In his old cabin, the area near the fireplace would reach 70 degrees while corners remained below freezing. In the new cabin, the warmest area measured 65 degrees, and the coldest area stayed above 40 degrees. The total heat energy in the space was actually lower, but it was distributed so evenly that the cabin felt warmer everywhere. Alistair was living in a space where he could move freely without encountering zones of intense heat or bitter cold. The fuel savings translated directly into time savings. In previous winters, Alistair had spent approximately 2 days per week cutting and hauling firewood. With consumption reduced by half, he needed only 1 day per week for wood gathering. That freed up an entire day for trapline work, equipment maintenance, or simply resting. Over the course of a 5-month winter, that represented 40 additional days available for productive activity. Other trappers began noticing differences without understanding their cause. Malcolm Fraser visited in early February and commented that Alistair's woodpile seemed remarkably large for midwinter. Most trappers were running low on fuel by February, rationing their fires to make supplies last until spring. Alistair's pile looked barely touched. Malcolm asked if he had cut an unusual amount before winter. Alistair explained that he had cut the same amount as always, but was burning it much more slowly because of how efficiently the cabin distributed heat. Malcolm was skeptical but interested. He asked detailed questions about fuel consumption rates. Alistair showed him the records, the daily measurements, the calculated savings. Malcolm studied the numbers carefully, then asked the obvious question. If the system worked this well, why wasn't everyone building similar setups? Alistair's answer was simple, because it required believing the system would work before you invested months of labor building it. Most men wouldn't make that investment based on theory alone. February 18, 1840, brought weather that would validate Alistair's system in the most dramatic way possible. A cold front moved down from Canada, driving temperatures to levels that few trappers had experienced even in the harsh Rocky Mountain winters. The thermometer at Cormac O'Neill's trading post registered 42 below zero on the morning of February 19th. The cold was so severe that exposed skin would freeze within minutes. Simply breathing the air was painful. This was survival weather, the kind that killed unprepared men and tested even experienced frontiersmen. Every trapper in the region retreated to their cabins and focused solely on staying alive. Fires burned continuously. Men wore every piece of clothing they owned. Survival became a matter of fuel supply and structural integrity. If your cabin held heat and you had enough firewood, you lived. If either factor failed, you froze. Declan Murray's cabin was built using standard methods: notched log corners, mud chinking, a single fireplace, adequate construction by all normal measures. But adequate wasn't sufficient when temperatures dropped to 40 below. Declan burned wood at an unsustainable rate, feeding his fire constantly to maintain barely livable interior temperatures. By the 3rd day of extreme cold, he had exhausted his wood pile. He had no choice but to venture outside in lethal conditions to cut more wood or freeze inside his own cabin. He made it to Malcolm Fraser's cabin a quarter-mile away and explained his situation. Malcolm shared what wood he could spare, but his own supplies were running dangerously low. The two men discussed their options. They could attempt to reach Cormac O'Neill's trading post, 2 miles distant, where emergency supplies were kept, or they could try to make it to Alistair's cabin, slightly closer, and ask for help. Malcolm suggested Alistair's place. If nothing else, they needed to see whether Mackenzie's Folly was keeping its builder alive in this weather. They arrived at Alistair's cabin on the afternoon of February 21st. The water wheel was still turning, its buckets crusted with ice but functional. Smoke rose steadily from the chimney, but not the thick black smoke of a fire being fed desperately. When Alistair opened the door, warm air rushed out into the frigid afternoon. He was in his shirt sleeves. The interior was comfortably warm, noticeably warmer than either Malcolm's or Declan's cabins had been, despite their fires burning at maximum output. Alistair invited them inside. The contrast was immediate and undeniable. The cabin's interior temperature was probably 55 to 60 degrees throughout. There were no cold corners, no frozen walls, no desperate huddle near the fireplace. The system was running exactly as designed. The fan circulated warm air continuously. The fireplace burned at a moderate rate, and Alistair's woodpile, visible through the window, was still substantial. Declan stood in the warm cabin and said nothing for a long moment. Then he asked the question that mattered. How much wood was Alistair burning per day in this extreme cold? Alistair checked his records and showed them the measurements. Approximately 1/16 of a cord per day during the cold snap. Declan had been burning triple that amount and still couldn't keep his cabin adequately warm. The extreme cold broke on February 24th, and temperatures returned to more typical winter levels. Declan Murray and Malcolm Fraser returned to their cabins, but something had changed. They had experienced firsthand the difference between traditional heating and Alistair's circulation system. The difference wasn't theoretical or marginal. It was the difference between desperate survival and comfortable living during the worst weather the mountains could produce. Malcolm visited Alistair's cabin again in early March, this time with specific questions about construction. How large did the water wheel need to be? What kind of bearings worked best? How was the fan system built? Could the design work with a smaller creek? Alistair answered every question without reservation. He wasn't protecting trade secrets or trying to profit from his innovation. He simply wanted other men to survive winters more easily than he had before building the system. Malcolm asked if Alistair would help him build a similar setup. Alistair agreed, but explained the scope of work involved. The foundation alone would take 3 weeks. The water wheel required specialized shaping and precision assembly. The mechanical coupling had to be waterproofed perfectly, or it would fail. The entire project would consume most of the spring and summer, delaying normal trapping preparations. Malcolm said he understood and wanted to proceed anyway. Losing 2 months of preparation time was acceptable if it meant not freezing during the next winter. They began work in April 1840 after spring breakup made construction feasible. Malcolm's creek was smaller than Alistair's, with less elevation drop, which required modifying the wheel design. They built a wheel slightly larger in diameter to compensate for reduced water flow. The construction process taught Malcolm exactly how much work Alistair had invested. Every component required careful measurement and fitting. Every joint had to be shaped precisely. There were no shortcuts that didn't compromise the system's reliability. Other trappers noticed the construction but didn't comment initially. Building a cabin was personal business. How a man chose to build was his own concern. But as the water wheel took shape and the mechanical coupling became visible, questions started. What was Malcolm building? Was this another version of Mackenzie's Folly? Malcolm's response was simple. He was building a cabin that would stay warm without burning excessive firewood. Anyone who doubted the concept should visit Alistair's cabin and see for themselves. Declan Murray didn't visit and didn't ask questions. But in late May, Alistair noticed him surveying a creek location near his own cabin site. The surveying continued for several days. Then Declan began clearing ground and gathering stones for a foundation. He didn't announce what he was building or ask Alistair for advice. He simply started construction using techniques that looked remarkably similar to what Alistair had developed. By summer's end, 3 cabins in the region incorporated water-powered circulation systems. Malcolm's was completed and functional. Declan's was partially built and would be finished before winter. And a French-Canadian trapper named Baptiste Moreau had started his own version on a different creek, using a design modified for his specific site conditions. Each new cabin, incorporating water circulation, demonstrated different adaptations of Alistair's core principles. The variations weren't copying, they were problem-solving. Each builder faced different creek conditions, terrain challenges, and available materials. The solutions they developed expanded the original concept in ways Alistair hadn't anticipated, creating a family of related designs rather than exact duplicates. Malcolm Fraser's wheel was 11 feet in diameter, larger than Alistair's, compensating for his creek's lower flow rate. He had also modified the bearing system, using wooden bearings with bronze sleeves instead of pure iron. The bronze was easier to obtain through trading posts and wore better under continuous use. His fan design used 6 blades instead of 4, moving more air at lower rotation speeds. The result was quieter operation with better air circulation. Declan Murray's system incorporated the most radical variation. His creek froze partially during the coldest weather, reducing flow enough that a wheel might stop rotating. He solved this with a dual power system. The water wheel operated during normal conditions, but he added a manual crank mechanism that allowed him to operate the fan by hand when water flow was insufficient. The manual operation was labor-intensive, requiring 15 minutes of cranking every few hours, but it kept air circulating even when the creek froze. Baptiste Moreau faced a different challenge. His creek had excellent flow, but ran through a narrow gorge that made positioning a wheel difficult. He couldn't build close to the water like Alistair had. Instead, he built his cabin 50 feet from the creek and extended the drive shaft using a series of supported bearings. The extended shaft required additional engineering to prevent flexing and binding. But once completed, it proved that the circulation concept could work even when the wheel was positioned at a distance from the cabin. The improvements weren't limited to mechanical modifications. Malcolm discovered that using a damper in the fireplace chimney improved heat capture dramatically. By partially closing the chimney during mild weather, more heat stayed in the cabin instead of escaping up the flue. The fan system then distributed this captured heat efficiently. Alistair adopted this modification immediately, adding a chimney damper to his own system. Declan developed a better waterproofing compound for the shaft coupling. He mixed pine pitch with rendered bear fat and charcoal dust, creating a seal that remained flexible in extreme cold while being completely waterproof. The mixture was easier to apply than Alistair's canvas and pitch method and lasted longer without maintenance. Within a year, everyone using water circulation systems had switched to Declan's waterproofing formula. The ductwork designs evolved as well. Alistair's original wooden ducts worked but were heavy and difficult to install. Baptiste built his ducts from canvas stretched over light wooden frames, creating flexible tubes that could be routed around obstacles and adjusted easily. The canvas ducts moved air just as effectively as wooden ones, while weighing a fraction as much. This innovation made installation significantly easier for future builders. By 1845, water-powered cabin heating had spread beyond the immediate circle of trappers who knew Alistair personally. The technique moved through the mountain community the way most frontier innovations spread, carried by conversation at trading posts, demonstrated through functional examples, and adopted by men who recognized practical advantages when they saw them. The system had no formal name. Some called it wheel heating. Others referred to it as circulation cabins. Most simply described it as building like Mackenzie or building like Fraser, referencing whoever had introduced them to the concept. Cormac O'Neill's trading post became an informal information exchange for the technique. Trappers, stopping for supplies, would mention they were planning to build a new cabin and ask if anyone knew about the water wheel systems. Men who had built them or seen them operating would share details, sketch rough diagrams in the dirt outside the trading post, and explain the basic principles. The conversations were technical and practical, focused on bearing design, waterproofing methods, and how to calculate wheel size for different creek flows. The adoption pattern was selective rather than universal. Not every trapper built a circulation system. The requirements were specific enough that many locations simply couldn't support the design. You needed reliable year-round water flow with sufficient volume and elevation drop. You needed mechanical aptitude to build and maintain the system. You needed willingness to invest months of construction time upfront for long-term fuel savings. Men who lacked any of these factors continued building traditional cabins, but for those who could meet the requirements, the advantages were compelling enough that adoption became almost inevitable once they saw a working example. The fuel savings alone justified the construction effort. A trapper who built a circulation cabin would save approximately 2 months of labor over a single winter compared to cutting wood for a traditional cabin. Multiply that across 10 or 15 winters, and the time savings became enormous. The improved comfort was secondary but significant. Living in a space with even temperatures throughout made winter isolation more bearable. The geographic spread followed the trappers' migration patterns. As the fur trade collapsed in the early 1840s, many mountain men moved to new territories. Some went to Oregon, others pushed into the northern Rockies or the Sierra Nevada. They carried their knowledge with them. A trapper who had lived through a Montana winter in a circulation cabin would build a similar structure in his new location if conditions permitted. The technique appeared in widely separated locations, each instance connected by the web of personal relationships that linked the frontier community. By 1848, when the California gold rush drew thousands of new immigrants west, some of those emigrants encountered abandoned mountain man cabins with mysterious water wheels attached. A few recognized the heating application and copied the design. Most simply wondered what purpose the wheels had served and moved on. But enough people understood and adapted the concept that it persisted in remote areas where fuel efficiency mattered more than construction simplicity. The innovation had become part of the frontier's technical vocabulary, a solution available to anyone who needed it and had the skill to execute it. Alister Mackenzie's name was sometimes attached to the origin story, sometimes not. The factual history mattered less than the functional reality. The technique worked, it spread, and it helped people survive in conditions that would have been significantly harder without it. Alister Mackenzie left the mountains in 1844. The fur trade had collapsed completely by then. Beaver populations were depleted, and silk had replaced felt in hat manufacturing, destroying the market that had created the mountain man era. Men who had spent decades in the wilderness faced a choice: stay and find new ways to survive, or return to civilization and build different lives. Alister chose to leave. He sold his furs, tools, and equipment to Cormac O'Neill, and used the proceeds to buy passage to Oregon Territory. He was 47 years old, scarred by weather and hard living, but still strong enough to start over. In Oregon, he established a small homestead in the Willamette Valley, farming land that had been wilderness 5 years earlier. The work was different from trapping, but no less demanding. He cleared timber, planted crops, built a simple cabin using traditional methods. The Oregon climate was milder than Montana. Elaborate heating wasn't necessary. He married in 1846 a widow named Catherine Ross, who had emigrated from Pennsylvania. They had 3 children over the next 8 years. Alister became a farmer, a neighbor, a member of a growing community. He rarely spoke about his trapping years. When asked, he would mention the mountains and the isolation, but he didn't tell stories about grisly encounters or dramatic survival. His past was simply past, not material for entertaining conversation. He died in 1867 at age 70 during the spring planting season. A heart failure took him quickly while he worked in his fields. He was buried in a small cemetery outside Salem, Oregon. His gravestone listed his name, birth and death years, and the phrase beloved husband and father. There was no mention of Montana, no reference to innovations or engineering, nothing to suggest he had changed how frontier cabins were built across thousands of square miles of wilderness. But in the mountains he had left 23 years earlier, evidence of his work remained. The cabin he had built in 1838 still stood, weathered but structurally sound. The water wheel had long since stopped turning, its bearings seized and wooden components rotted. But the foundation was intact. The elevated platform remained level, the mechanical coupling through the wall, though no longer functional, showed how the system had worked. Similar cabins existed throughout the northern Rockies. Some were still occupied. Others had been abandoned as the region's economy shifted from furs to mining to ranching. A few had been maintained and improved by people who understood their value. The water wheels turned in places where no one remembered Alistair Mackenzie's name, moving air through cabins where families lived more comfortably because of engineering principles developed by a Scottish trapper obsessed with heat distribution. The revolution Alistair had started was silent because revolutions in practical technology usually are. They don't announce themselves or demand recognition. They simply make difficult things slightly easier, dangerous situations slightly safer, hard lives slightly more bearable. A cabin that stayed warm using half the firewood didn't seem revolutionary until you spent a winter in one. That realization, repeated across dozens of individuals, changed how people built and lived in remote places. The change was permanent, even though the inventor was forgotten. The engineering persisted even after the engineer died, and that persistence, silent and uncelebrated, was the truest measure of success.